Welcome to the video. In this video we're going to talk about radio systems. This is intended to be an introduction to radio systems for those of you who are new to remote control or coming back into the hobby after being away for a while. And we're going to talk about each of the parts of the system in turn. We're initially going to talk about the radio and how the radios work, the different modes, mode 1, mode 2. Then we're going to talk about how the radio talks to the radio receiver, so how that all works. We're going to talk a little bit about binding, why binding is used and what it does. As part of that, we'll talk about what failsafe is, because a number of these receivers will not only bind to the radio but also remember the channel positions if they lose the connection, and that's important, and we'll cover why. Then we'll actually talk about connecting the receiver to things like servos and motors with speed controllers, and how all that works together, and how this little receiver is talking to the speed controller and the servo, so that if I move the throttle, the motor's running, and if I move the elevator control, the servo is moving as well. So we'll cover all that in this video. It's not intended to be an in-depth look, but the idea is that you're coming back to RC or new to the hobby, you can watch this and know enough to understand some of the acronyms that you're going to read on forums, and also understand what some of the other people are telling you when you're trying to explain problems to help troubleshooting. So the first place we'll start is how the basic system works. You'll notice that all that's really happening is the radio is translating the movement of one of the controls into the movement of either a servo or the amount of throttle that goes into a motor. And that is all the radio system is doing. All of the other fancy stuff on a computerized radio, the menus and everything else, is all about how those two interactions work. How much you have to move the stick to move the servo. How much the servo moves at each end of the stick movement. But very basic principle, as you move the stick, you move the servo, or if it's connected to a speed controller, the control will look after the throttle. So as you see, I increase the throttle, you'll hear the motor get faster and faster. And then slow down. And you'll see as I move the stick, you'll see the servo rotate. And the other way, like so. So first of all, let's talk about modes and what the modes are on the radio. So the four modes that you'll come across are on the screen now. Modes 1, 2, 3 and 4. My radio is a mode 2 radio, which is very common in Europe and North America, where it's the throttle on the left hand side along with the rudder, and the elevator and aileron on the right hand stick. You can occasionally get radios that will allow you to swap the modes, and every time you swap the mode you also have to swap where the spring loading is, because obviously you don't want the throttle spring loaded, you want it to stay where it is for safety purposes. So just be aware, if you're in the forums or you're looking at a listing and it's talking about a mode 1, mode 2, 3 or 4 radio, this is the little diagram you can refer to figure out where everything is. Once people learn with the radio, that tends to be the layout that they will stick with for the rest of their flying career, so it's important to use the right one from the start. So if we look at my radio here, the way this works, it's set up so we only have two things connected. The throttle control obviously controls the motor. The rudder, i.e. on the tail of the plane, which makes it turn in the air, is on this stick. On this stick over here we have the elevator, which makes it rise at the model rise and fall, so the nose goes up and down based on that control. So that would normally be connected to the elevator at the back of a plane. And then you also have the aileron control, which is what makes the model roll from side to side. So now we kind of understand that, the next thing we probably talk about is how you bind the radio to the receiver and what that means and why we have to do it. So now we're looking at a slightly simplified version of what we had before. So I've taken away the motor and the speed controller because we don't need that to illustrate binding and failsafe. But we still have the servo connected to the elevator control on my radio, so I move the stick upside down, the servo goes one way or the other. and if I reverse the channel, then the servo would rotate in the opposite direction from each of my stick movements. Now what you've noticed is that I've had to also put something else new on the table. So the way it's working is this little battery eliminator circuit, which is actually part of the speed controller that I've taken off the table. There's actually one of these inside here, so that's why we didn't need it before. This thing is providing the 5 volts that's powering the receiver, and also providing the 5 volts that come out of the receiver down this cable and into the servo. So that little box of tricks is giving a nice steady 5 volts that's giving my receiver and the servo all the life they need. And then I'm connecting via my radio wirelessly to the little aerials on the receiver. So as I move my stick, the servo moves as well. Now the frequency of the connection between these two radios is actually 2.4 gigahertz, and you'll hear that talked about on a lot of different forums. But I'm using Spectrum equipment here. Everybody has their own favourite, whether it's FR Sky, Tyrannus, Hobby King. Everybody has their own particular version of it. Futaba, and this just happens to be the one that I have. A lot of the systems use 2.4 gigahertz to talk between these two parts, but actually are using a different language. So it's like if you imagined that this radio is speaking English and this radio is speaking English, they understand each other. If this was a Futaba receiver, the Futaba, you could say for example, was speaking Spanish and this radio was speaking English. So in that case, even though the radio was transmitting at the right frequency, the receiver wouldn't understand what it was saying. So you have to make sure that the receiver is going to work with your radio. Most modern radios, when you buy them these days, will come with one of these receivers in the kit. In the early days of remote control, the way that you got a receiver and a radio talking to each other, once you knew that they understood the same language, Spanish, English, German or whatever, is that you would put them on the same frequency. And there were particular frequencies, and the way it worked is that when you went to fly, you would be given a particular frequency that you could use for your flying time, and you had a little radio crystal that you'd plug into the radio that would change the frequency that you were transmitting on. There would also be a crystal that went into the receiver, and that would be the way that you would talk to each other. The danger of that, of course, was because if you had somebody else with the same frequency, then your receiver could hear both radios at the same time, and that could cause mass confusion and result in a crash. The spectrum frequency technologies that most of the modern radios use these days not only use 2.4 gigahertz and different bits of the 2.4 gigahertz band, but are also using digital communication to make sure that the signals that are received in the receiver are right and are error checked. So if anything wacky goes on with the radio, the receiver knows about it. And this information is sent in frames or packets of information around. Now I'm not going to go into too much detail about how all that works. If you're really interested, you can look at the wikis and Google it and find out about it. But suffice it to say that the radio and the receiver, I'm not just sending one continuous stream of positions, I'm actually encoding the information digitally, surrounding it with error checking code, and then it's going out to the receiver. And if the receiver and the radio, when they power up, have a noisy environment, they'll hunt around on the 2.4 gigahertz frequencies they can use until they find one that works. The result of all that complexity is that most of the time you turn your radio on, you get the light on your receiver, you have a great solid connection, and you're good to fly. Even if there are other people around with identical radios and identical receivers, because not only is the radio on the 2.4 gigahertz and they're both speaking the same language, but most importantly, they have a secure connection between the two. So you can't accidentally turn your radio on and it bind to your friend's receiver in their plane or multi-rotor next to you. The process of making that connection between your radio and your receiver is called binding. You only have to do it once, and once it's done, then these two are a pair and they will only talk to each other, and this will only activate when the radio turns on. So to illustrate the point, if I turn this radio off, you'll see that the receiver will realise the radio is no longer there and take the connection light off. If I turn the radio back on, it'll take a second to connect, and there we are, we've got our connection back again. Now, we need to talk about how we do the failsafe and also what that means, but first of all, let's go through the process of binding the receiver to the radio. So we'll bind the radio to this receiver again, and not only are we binding the radio and the receiver, we're also binding the receiver to this radio with this specific model memory. Now, that's important, and it's a fail-safe feature, so that if you have a different model selected to the one that was selected when the bind happened, this receiver will not power on and activate. And that's great. If you had two models on your radio, one was for maybe a quadcopter, the other one was a flying wing, you'd only want the flying wing to activate when the flying wing model had been selected on your computer radio and vice versa. In Spectrum World it's called model match, but every manufacturer pretty much has their own version of it. So first of all, let's make sure we're on the right model memory. It's called test rig. This is the model memory I use for all my bench testing of models. So we'll set this one up. We're going to rebind this receiver to the radio, and I'm going to go through the process for Spectrum. Now, every manufacturer's process is slightly different. Look in the manual or look online with the bits and pieces that came with your radio, and it will talk to you about the specific process. But this is how it does for Spectrum, and it's very similar for most other manufacturers. The thing that we're going to need to make this happen is we're going to need something called a bind plug. Now, a bind plug is a special plug that will go into one of the ports of the receiver, and it's usually clearly noted as battery or bind, and we're going to pop that special bind plug into that port, and then we're going to power the receiver on. And what you'll notice is that the receiver will start flashing like crazy. That means the receiver is just sat there waiting to hear for a connection request from the radio. So let's bind to it. The way it works on this radio is you have to press and hold this button on the back as you power the radio up, and then once that process has started, you let go of the bind button at the back, and the bind is successful. We'll confirm it all works by turning the radio off, and there we are, that all looks good. So now we'll power down the receiver, take out the bind plug, power the receiver back on, and we'll turn the radio back on too. We'll get our connection light, and now that is connected. If I changed the model on this radio and tried to power it up, it wouldn't connect to this receiver as that failsafe function. Brilliant, that's great. Now if I turn the radio off, we'll lose the connection light and the system will fail safe. Now the reason it's flashing red there is just to let me know that it's lost connection with the radio. So that's binding, that's the way it works. So we have to bind each of the receivers to the radio and the specific model memory that we're interested in. Now, the next thing we'll do is let's actually rebind this, because not only do receivers store the connection and the security handshake between this receiver, the radio and the model memory, but a number of receivers also have failsafe. Now what failsafe is when the receiver first boots up, it has to be sending something out of all these channels while it's waiting for connection to the radio. And also, in the event that it loses the connection with the radio, like it just did while that little red light was flashing, it also needs to continue to send out a set of positions for the servos and a position for the throttle so that the plane, or whatever it is you're flying, will continue. Or send a specific level out so that the flight control board in a multicopter can realise there's something wrong with the radio and take appropriate action. Now, as you saw, the way it worked is nothing happened to the servo before, because the mid position where the stick was at was the position that was saved when the bind happened. But watch what happened if I bind it with the stick in a different position. So let's rebind it again. Let's put the bind plug back in the port. Let's power up the receiver. We'll get our flashing light. Let's turn the radio off. So there's our flashing bind light. This time I'm going to bind it with a servo, or with a channel that runs the servo at this low position. So it's a little bit tricky, but I'm going to hold that stick in its lowest position. I'm going to press the button at the back that will start the bind, and I'm going to turn the radio on. Let me hold it all until the bind happens, and then let go. Now we have it bound again, and we have control of our servo, but this time watch what happens to the servo when I turn off the radio. Because when I bound the receiver and the radio together, I had the stick in the low position. That is the position that the failsafe sends all the controls to. And that's what failsafe is. So failsafe is what happens on the receiver when it loses a connection. It sends those positions on all the channels to all the servos and all the speed controllers, or it sends all those bits of information to the flight control board on your multi-rotor, and you have to be very careful about failsafe if you have it. If you don't have it, the danger is that the radio continues to send the signals that it had when the connection was lost. If you were at full throttle in a dive when the radio went off, the model will continue full throttle in the dive right until it hits the ground. And you'll occasionally hear about something called flyaways on the forums, and that's sometimes what will happen. If the radio connection is lost and there is no failsafe set up on the receiver, then wherever the sticks were when the radio connection failed, the receiver will continue to power the servos and speed controller at that level and those positions that you had it on, and continue to fly the plane right out of sight and right out of your life. In a failsafe, what you'd probably do is you normally make sure that the failsafe is always, the throttle is off and all the positions of the control surfaces are neutral, and at least that way if the radio fails, then the plane will shut down its throttle and land safely, or glide without going too far. So that's binding and that's failsafe. Next thing we talk about is how all these connections work, because you've probably already noticed that we have different colour cables. So let's have a look at these cables that we've been talking about. Now they're both servo cables in the end in these three connections, and we'll talk about what each of these cables do in a minute, but very simply, one's a ground, one's a +5 volts and one's a signal. And you can see there are two different colours. This one is the one that's connected to the servo that we've been using in the video so far, but we also have this one here, which is connected to the speed controller that we're using to power the motor. And that has three colours as well: red, black and white. And again, one's ground, one's +5 volts and one is signal. If you actually look on the individual receivers themselves, this one's actually slightly easier. This is a 6-channel. You have the battery bind at the bottom, and then it goes throttle, aileron, elevator, rudder, gear, and then auxiliary 1. And each of those channels correspond to one of the controls that we were just looking at. The throttle, aileron, elevator, and rudder are on the sticks. The gear and auxiliary 1s are typically separate switches. And you can see here that you just plug in the speed controller into things like the throttle, and then you'd plug in servos if it was a plane into the elevator rudder. Now on the side, normally there is a little indicator. I don't know if you can see on this one, it's super easy to see. I'll try and get it so it catches it. There's a little S, and that is showing you which is the signal pin. So on this one, the top pins on this connector is signal, the middle is +5 volts and ground. So if you look at that in a quick diagram, here we have our receiver that we've just been looking at. We have a battery bind, throttle, elevator, aileron, rudder, gear and auxiliary 1. So this has actually got the 6 channels, and here are the 2 pins. So you can see the top one, there's the white one, the black or brown pin is usually ground, the the middle pin is always plus 5 volts, and the yellow or white is the signal. So the way you install this, remembering that the S is showing us the top row is the signal. If we're plugging in the servo, then obviously we need to make sure that the signal cable, which is orange, is plugged into the servo lead. So let's plug that into the elevator channel. And the connection to the speed controller, that is going to go into throttle. And again, we want the signal lead, which is white, at the top, so that that is connected properly too. And that's how you connect them up in your model. Pretty straightforward stuff. Some of the receivers though, like this one, this is a 7-channel receiver from Hobby King. This one interestingly doesn't have Failsafe, so you have to be a bit careful, but it has a longer antenna, and that's handy if you're going to put it inside something like a carbon fibre plane or chassis. These little stubby aerials are fine, and the reason there's 2 is it kind of gives you what's called diversity, so depending on the orientation as you fly the craft around, it gives you 2 chances of getting a good signal. With this one, this big long wire is supposed to come outside of a carbon fibre frame. The reason being is that carbon fibre kind of absorbs the radio signal that's coming from the radio, because 2.4 gigahertz doesn't go through things very well at all. But here you can actually see you've got the different channels listed out. Now they actually are going to be pretty much the same as the ones on this other receiver, but on this one you have to find your manual and figure out which is which. Now we have connected up, that's great, but there's also other things that you'll read about in the forums. First one is how you connect these up. So just like we're connecting up here, we can connect each of the individual servos and each of the individual connections into the channels that we need. This is called PWM, or pulse width modulation. And here's a couple of images of receivers that I've got installed on my craft that are using PWM, where each of the individual channels go via a separate cable to where they're needed in the craft. Even things like into flight controllers for multi-rotors, things like quadcopters, hexcopters, etc. So the way that looks is that you plug a cable into each of the individual channels that correspond to one of the controls on your radio, and then you connect that to whatever it's going to be. So for example, if it was a plane, the throttle's going to go to the speed controller for the motor, then the elevator is going to go to the servo that controls the elevator at the back, the aileron is going to connect to the servos out in the wings that control the ailerons, the rudder again is going to connect to the servo that connects to the back, which moves the vertical rudder, and then the gear and auxiliary switches will connect to whatever you want them to. It might be something like landing gear or lights or whatever. That's PWM, or pulse width modulation. That's a very common way of putting things together. The great thing about this is that when you have lots of separate servos and speed controllers that you need to plug in, this is a really simple, easy way to do it. There's also a couple of ways to get the signals out of your radio receiver into the craft itself. Now, there are 2 versions of this. I'm going to talk about PPM, or pulse position modulation, or CPPM it's sometimes called as well. And CPPM or PPM uses one single cable, and you'll normally notice, like for example on these receivers, these are the Hobby King R615X's. If I plug a cable into the battery bind port, that is where my PPM signal comes out of, and that is all of the signals for all the other channels, one after the other in a big long stream. Now obviously the thing you connect it into is usually a flight control board for things like multicopters, and the flight control board needs to be told which order those signals are coming in on, but it vastly simplifies your cabling because you only have one cable that goes from the battery bind into the craft. So here's a picture of one that I did with the NAS A32 in one of my series of videos. There's other versions of this which allow you to use a single cable to transfer all of your control positions to one place, and that's called SBUS. And SBUS is kind of like PPM, but actually it is a slightly different implementation, so you can't use PPM and SBUS together, but both of those allow you to use a single cable to get all of your controls out of your receiver without having to have 6 or 7 wires all over your model. Next thing to talk about then is how do we actually get the signal from the controller on the receiver to something like the speed controller or the actual servo itself. Well, the amazing thing is that it actually is sending out little microscopic pulses on each of the channels, or if it's PPM, on one individual cable. Now when I plug the servo into the receiver, what happens is down that signal wire, the receiver is sending little pulses that are in direct relation to the position of the control on the radio. So the receiver hears that the elevator is in the middle position, and it sends a little pulse down the wire that's exactly 1500 microseconds long. And the servo hears that and says, that means I need to be in my middle position. 1000 microseconds meaning a low position on the control, 2000 microseconds meaning a high position on the control. So there is a little bit of electronics inside the servo that understands and is measuring the width of the pulses, hence pulse width modulation, PWN, and positioning the servo in relation to the width of the pulses it's getting. Similarly, the speed controller is doing exactly the same thing. When we plug that into the throttle channel, the receiver is sending out the pulses in exactly the same way, and the speed controller is then taking that pulse width and then converting that into a power setting for the motor. And that's actually how it works. So now we can start at the radio. So we position the radio controls where we want them to. The radio then sends that information securely over to the receiver. The receiver then receives that and then sends out on each of the channels, or if it's PPM on one cable, pulses that are in direct relation to the position of the controls that it's heard. And there is little brains inside the servos and the speed controllers which then convert those pulses back into meaningful information and use them to either position the servo or to send more or less power to the motor. So sometimes you'll see when you're setting multi-rotors up that there will be a range for maybe the throttle channel, and you'll see ranges of things like 1060 up to 1860. It's very common for things like Simon K speed controllers. That's what they're talking about. It's actually the width of the pulses that are coming from the receiver, which is in direct relation to the position of the controls. So normally on most radios, 1000 is the low end, 2000 is the high end, and 1500 is in the middle. And if you connected an oscilloscope to one of these channels and you actually moved the control on the radio, you'd actually see that pulse width changing all the time. We have covered a lot. We have talked about the radios, we've talked about the modes, we've talked about how the binding works, what failsafe is, we've talked about what pulse width modulation is, how that differs from things like PPM or CPPM. We touched on SBUS, and now we've talked about how all the connections work and how the receiver talks to things like the servos and the speed controllers in your model. So hopefully that was enough of an introduction to help you understand the 3-letter acronyms and some of the bits and pieces in the forums that you're going to read. If you have any questions or comments or something that you need help with, please post them below. If you'd like to know more about remote control information, I have a special introduction to remote control an introduction to power system playlists on my channel. Please find those. In addition, I also have a number of videos that I'm just going through now. I'll put the links to these down in the bottom of the description, and if you want to go and find out more about introduction to LiPo batteries or radio systems or FPV or any of those extra pieces, you can watch these other videos, and they're written and presented in the same way, so that it's trying to present the complicated subject in hopefully easy to understand slides and visuals. Thank you for watching. Please like, subscribe, and happy flying.